Now we will see a very interesting thing, that is a Carnot engine. Yeah, so it's a theoretical engine that operates on the Carnot cycle. So it's not you can say that the practical one, it's an ideal one. Yeah, so that's why it's called as the theoretical engine. Yeah, so that means it is a reference one. So here is the source at T1, insulating stand, again the sink at T2. So this is nothing but the working substance which is put in this cylinder. So the base is nothing but you have to make it conducting, and the cylinder with a conducting base. Yeah, so this conducting base and the wall should be your insulating. So how we are just see the working for this your Carnot engine. So there is a cylinder, yeah, so in which that gas has been put, the source is there, the sink is there, the working substance, the insulating stand over here. So all this consists over here for this case of your Carnot cycle. So this Carnot cycle, so the isothermal process, the isothermal expansion for the first step. Yeah, so the first you have to move it, the first step over here. So just put this base, yeah, at this source at T1. So there is an exchange of heat. Yeah, so definitely there is an exchange of heat between this source which is at T1 and this working substance. So definitely the heat is going to get by those molecules, and obviously it's just going to expand it. So this is nothing but the process of your expansion, so from A to B. So this is the first step where you can say that the expansion of occur. So the temperature remains constant, since obviously the heat is getting exchanged, so it is a slow process. Yeah, so it is a slow process. So this is a isothermal expansion, and the temperature obviously again which is same over here. So this is P1 V1, then the next one is you can say that it is P2 V2, keeping the temperature constant over here. Now when you move it from B to C, so when you move it from B to C, now keep it on that insulating stand over here for this particular case, insulating stand. So again this is the insulating stand, so there will not be any exchange, so this gas will further expand. Yeah, in the second case we are not providing any heat, but still it is going to expand over here. So delta Q is 0, so definitely you can say that again it is the adiabatic expansion. So the volume is going to again that is increased, which is going to increase from your V2 to V3. Yeah, so V2 to V3 has going to just volume is going to increase, the pressure will drop down, since it is expanding the pressure will drop down, and again the temperature will move from that is your T1 to T2. Yeah, so again the T2 is less and T1 is greater for this particular case. So which is what we call it as nothing but your adiabatic expansion, so which is your second step. So first is isothermal, and the second one for this particular case that we will call it is nothing but your adiabatic expansion for this particular case over here. So in the third case again that is a isothermal compression. In the isothermal compression, so again this is your isothermal. Yeah, so isothermal compression, so you are going to compress it. So again, so that is nothing but the sink, so which is at lower temperature. Yeah, so again this is at lower temperature, so this is nothing but the isothermal compression. So you are just going to compress it. Yeah, so you are going to compress it. So when you just compress the gas in the third case, yeah, so in the third case again we will say that, so this is how it will occur. So after compressing, so definitely its volume is going to now increase, and definitely again for this particular case over here, so this pressure is going to increase, yeah, and volume is going to decrease for the case of your this isothermal compression. And again, so this is isothermal, so making that temperature constant. So this is your third step of your isothermal expansion, so where the temperature drops down, and that's why here that Q becomes negative for this particular case over here.